All right, welcome back to another calculus lecture. In today's lecture, we begin the second sort of fundamental concept in a typical Calc 1 course, and that is the concept of integration. So to motivate this, I want to do something similar to how we motivated the derivative. So recall, to motivate the derivative, there we go. We asked a particular question. So we asked essentially, given a position function, so that is maybe I have a function that's governing a car traveling down a racetrack. I think that was the example we used. Given a position function, how do we compute velocity, and in particular instantaneous velocity? So if you give me a function and ask me how fast the car was going based on their position at particular times, well, we needed to come up with the concept of a limit and then the concept of a derivative in order to actually make that notion precise and to understand how to actually compute that. So in the same way, the question that I want to ask now, so guiding question, so instead of being given a position function, let's suppose that now we're given a velocity function. So given a velocity function, how do we compute what we want to compute is the distance traveled, so the total amount of distance that I cover over some time interval. So compute distance traveled. So if you tell me that if you give me your speed at any particular time, and I have this data available to me over the course of, say, 2 hours when I'm traveling from Manhattan to Kansas City, then I should be able to use that velocity information to compute the total distance that I have traveled. Okay, so how do we do that? What exactly would be the process? As we'll see, and this was sort of Newton's insight as well when he was developing calculus, these questions are intimately connected, and they're very similar to one another. You can sort of already see the similarities in how you might go about approaching this. So what I've got here are a couple of examples that I want to sort of work through. So suppose that I have some velocity information about, say, a car, maybe. T maybe is in minutes, and velocity is in, I don't know, miles per minute or something like that. Maybe hours and miles per hour would be more natural. But say at these particular time moments, 2 minutes after I start, 4 minutes after I start, whatever, these are the speeds at which I'm going. So if I had this, well, how do I compute, or at least estimate, maybe we'll save exact computation for later, but how would I estimate the distance that I've traveled? Well, first of all, we can start with a lower bound. So if I want to estimate something, I can try and estimate it from below and above. So maybe let's do a lower estimate. And we'll reason as follows. So notice that between the time interval 0 and, or the time interval between 0 minutes and 2 minutes, I am traveling at least 20 miles per hour. And I should say, suppose a car travels with increasing velocity. So these numbers, once they sort of hit 20, this number doesn't dip back down and then come back up to 30 spontaneously. It's it's just a smooth sort of increasing curve as we're going along like this. And that'll be the setup for both of these. So between 0 seconds and 2 seconds, I'm traveling at least, or minutes, we're going to stick with minutes here because I'm going to keep messing that up, and this is going to be miles per minute. And maybe we're talking about a rocket ship instead of a car, because you're not traveling 20 miles or 30 miles an hour, 30 miles a minute in any sort of car. Whatever. Doesn't really matter. So between the time markers 0 minutes and 2 minutes, I'm traveling at least 20 miles a minute. So that tells me that, well, for each of those minutes, I travel 20 miles. And so in this time interval, I travel at least the number of minutes times the lower bound on the time, or on the speed that I'm going throughout that interval. And I can do this same sort of analysis through each of these intervals. So between 2 and 4, it would be the difference between these two time intervals times the lower bound for the speed that I'm traveling at, and then so on and so forth. And this, whatever this number comes out to be, will be our lower bound. And if we actually were to compute this, I've done this ahead of time, this is going to be exactly 360 miles. Now, that's a lower estimate. Well, we can reason the same way and get an upper estimate. So upper estimate. Now, if we wanted to do it with an upper estimate, we would use the upper bound for how fast we're traveling. So between 0 minutes and 2 minutes, we're traveling at most 30 miles per minute. And so throughout this whole interval, we can sort of give an upper bound of the distance traveled during that interval. And then we do the same thing for each of the other intervals. Just like this. And again, I've worked this out ahead of time, and this is going to be 420 miles, blaze it. So we have an upper and a lower estimate, so we can say that that 360 miles is less than or equal to my distance traveled, and this is less than or equal to 420 miles. So, in terms of orders of magnitude, we're in the ballpark for about, how far we traveled. And this is using only velocity measured every 2 minutes. Well, you might ask, well, what if I have a more accurate velocity measurement? Maybe instead of every 2 minutes, I have my velocity every 1 minute. And this is exactly the same data, but just filled in at the odd minute markers here. So we can do the exact same analysis. So my lower estimate. Now the distance between, or the intervals that I'm looking at do not have a length of 2 minutes, they have a length of 1 minute. And so 1 minute times my lower bound of 20 miles per minute here. And then we just go along and do the same thing. I'm not going to write out everything. But we would get all the way up to 49. We don't, when we're using a lower bound, we don't count the last one like we did up here. We didn't use 50 right here. So my lower estimate now, and again, I worked this out ahead of time. So this is going to be 376 feet. I'm sorry, not feet, miles. And same thing, I can do an upper estimate. So for this first interval, I'm traveling at most 26 miles per minute. And so I have 1 minute times 26 miles for that minute, plus 1 times my next interval, I'm traveling at most 30 miles a minute, so on and so forth. Here, notice we skipped the first mark, or the first velocity, because we're doing an upper estimate. And we get all the way up here to 50. And this is going to be 406 miles. And notice what's happened. The sort of interval size here, notice there's a difference of 60 miles right here. Now, there's only a difference of, oh, how much is this? 34 miles here. So from this data, we know that the distance traveled lies between 376 miles and 406 miles. And so we've made our estimate better. The distance between our two estimates has decreased by making by having a more accurate table of velocity values. Okay, so and you might ask, well, what if I had an even better table of values, a more accurate table of values? And indeed, what you would have happen is that these two numbers would get closer and closer, and if your velocity was perfectly measurable, you could theoretically compute the exact distance traveled. Okay, and this is going to be the entire idea behind integration. So with these examples, I want to graphically or sort of geometrically illustrate what's happening here. Because I think this is very instructive and very important to sort of do this. So we're going to use this same sort of idea. I've got two graphs of this velocity function drawn. They're not exactly the same because I'm not perfect. But let's go ahead and just graphically illustrate what each of those computations was. So this first one, we're going to use the less accurate of the two estimates. So here, let me get a couple of colors here. So we'll do our lower estimate in blue. So what did we do for the lower estimate? Well, let's say for the interval 0 to 2, we took the lower velocity and used that throughout the entire interval and computed the distance traveled by multiplying the length of the time interval by the velocity. Well, geometrically, what are we doing here? We're actually just computing the area of a rectangle, like so. Right, I took my lower bound of 20 and used it throughout the entire interval, and then my interval had length 2, and so the area of this corresponds precisely to the distance that I traveled throughout this interval. Okay, and then we can continue this picture. And so the area here corresponds to the lower estimate. Lower estimate. I shouldn't say is about, but whatever. The lower estimate for our distance traveled is precisely just the area of these rectangles here, added all up, right? Because what we did is we computed the area of each one of these, and then we added them up. Well, the same thing holds for the upper estimate. And for the upper estimate, instead of using the lower bound, we use the upper bound. That is the right endpoint of this interval here, where it intersects the graph of v of t. And so, if I want to draw that, and so you see that the pink area, or the red area, I'm not sure how it comes through on the camera, looks pink. The pink area is going to give me an upper bound. The area of the, if I add up all the pink rectangles, you know, if I shade all of these pink and then add them all up, that's going to give me exactly what we computed before as our upper bound. Okay? Now, you might ask, what happens when we increase the accuracy of our velocity measurements? Well, let's go ahead and see how that works out. So if I draw my graph here at each one of these markers, and I'll cut the video so it's not too long here. Okay, so this is the new graph of our increased accuracy for our velocity function. So notice what's happened here. My blue is still a lower bound, my pink is still an upper bound, but the difference between the two is actually much smaller, and it looks more and more like just the actual area underneath this graph. Okay, and so the sort of main takeaway from this is that if I have a velocity function and I want to compute the distance traveled over some particular time interval, then really what that corresponds to geometrically is actually just the area underneath the graph of the velocity function. So let's go ahead and write that down as a key idea. So distance traveled corresponds to the area under the velocity graph. Okay, so this is going to be our whole motivation for defining the integral, and we're going to do that in the next lecture. But yeah, this is the main idea here, is that in order to compute distance traveled, it suffices to actually just do this geometric analysis and figure out what the area underneath the graph should be. Okay. Now, one of the things you might ask is, well, what about what if my velocity like somehow goes negative? So what about, if I have something like this, here's my velocity and it does something like that. This is t, this is v of t. Well, now what does this represent? Well, you can think about velocity as having a direction. So velocity has a direction. And so if this is the graph of velocity, then when it's positive, you can think about traveling in the positive direction. We might define that as up or right or north or east or something like this. And then when it's below the x-axis, you can think about this as traveling in the negative direction. So maybe this is south or west or down or left or something like this. So the area underneath the curve is going to be sort of backtracking. So you're going to travel some distance over this interval, and then over this interval, you're going to travel in the opposite direction. So from here to here, we travel in the positive direction, and from here to here we travel in the negative direction. And so if you were to do the same sort of analysis with drawing these rectangles, some of those rectangles would actually have to be below the axis here. I might have something like this. If I'm trying to estimate my function, this area below the graph is going to subtract from this area here when we're traveling in the positive direction. And so we can think of area under the graph as the sort of net distance you travel. So all the positive plus all the negative. So it's possible to sort of wind up in the same place, but you can compute this by doing this sort of area analysis. Okay, so we shouldn't be too scared when we see negative area. It just means that you're changing the direction in which you travel, or whatever the appropriate analog of that notion is in the problem you're studying. Okay, so the last thing that I want to do is a quick example which hopefully will clarify these notions of positive and negative distance and how we might think about these things. So the velocity of a particle, is graphed below. And the positive velocity is just going to mean it's going up. So you can think about a particle sort of traveling in just up and down in a straight line. So positive velocity means up. And negative velocity means down, obviously. Okay, so I want to do two things. So one, compute the total distance traveled by the particle. And two, I want to indicate the final position of the particle. Okay, so I'm going to use a graph to compute the total distance traveled, and then I also want to indicate the final position of the particle. So let's go ahead and get the graph of a particle, the graph of the velocity of a particle. And we'll do something not too challenging, because this is supposed to be illustrative. So 1, 2, 3, 4. Yeah, something like that. So let's say the particle does something like this. And we're going to have this be 3 feet per second, 6, 9, negative 3 feet per second, negative 6, negative 9. And let's say the particle increases its velocity from its starting point. So it's going to start at rest and then increase spontaneously. And then we're going to decrease back down to 2. And we'll stay 0 for a while. We won't move. And then we're going to decrease a little bit and then increase a little bit back up to rest. So the velocity of my particle just sort of increases to 9 feet per second, and then it decreases back to being at rest, and then it's at rest for a little while, and then it backs up in the negative direction. It goes negative 3 feet, goes down to negative 6 feet per second, and then back to rest. Okay, so I want to compute both of these things here. So how do I compute the total distance traveled? Well, that's just going to be the total area underneath or between this curve and the axis here, between the x-axis. So total distance is equal to total area. And we're going to indicate that this is regardless of sign. And by sign, I mean it's negative area if it's under the x-axis and it's positive area if it's above the x-axis. So what I'm going to do is just compute these two areas and then add them together. And that's going to be the total distance that I travel. Well, I can do that geometrically very simple. So I have two triangles here. So this is equal to, well, to compute the area of a triangle, it's 1/2 the base times the height. So the base is 2, the height is 9, so this is going to be 1/2 times 2 times 9. And then I'm going to add the other area that of this triangle right here. So the base is 1 and the height is 6, so this is going to be 1/2 times 1 times 6. And so this is going to be 9 plus 3, which is 12 feet. So in total, it travels 12 feet. If I were to neglect direction and just want to quantify the total distance that I walked, or that this particle traveled, that's going to be a total of 12 feet. Even though you sort of went one way and then started going the other way, you traveled a total of 12 feet. Now, to do the other part, in order to indicate the final position of the particle, we need to take into account the signs of these areas. So what we're going to do is say that the final position, and this will be relative to its initial position because we don't know its initial position. Position equals, this is going to be the sum of the signed area. So now I'm going to add the positive area and I'm going to subtract the negative area, subtracting the distance that I sort of came back when I started backtracking. So minus 1/2 times 1 times 6. And the same sort of computation up here gives that this is 6 feet. And 6 feet, this is positive, so 6 feet above the starting position. Because we don't know exactly where we started, but we know that in total, I traveled 6 feet in the positive direction away from my starting position. And so that's going to be up, as we indicated in the problem. Okay, so this is how we can use a function to estimate these sort of interesting quantities, natural questions that you might want to know in various scenarios. So in the next lecture, we'll talk about how to do this with more general functions. So here we have nice sort of linear segments. Well, we don't always have that, obviously. So what are we going to do? And this is the sort of main thrust of the idea of the integral. Okay, so see you all in the next lecture.